Welcome to the third presentation in the sixth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the third webinar of our sixth series, which we hope to continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the sixth series will be distributed through the IAS mailing list, Twitter, and our LinkedIn page. Today's webinar will be given by Dr. Roberto Mennitto at SINTEF Industry in Norway. I am Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by Giuseppe Pizzella at Saudi Aramco R&D in Saudi Arabia. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 per year, to support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @IntAdSots for future updates regarding IAS events, webinars, and information about scientific meetings. We also have started a LinkedIn group, which can be found by searching the International Adsorption Society. Please help us expand our YouTube channel by liking this video and subscribing. We would like to remind the attendees of the 15th Fundamentals of Adsorption Conference that is being held this year in Porto, Portugal, between May 18th and the 23rd. Early bird registration is open now until this Saturday, March 1st. To repeat, just a few more days to get the early bird pricing. Additional information can be found at the URL given on the slide. We look forward to seeing everyone there later this year. I'll now hand it over to Giuseppe, who will moderate the YouTube Q&A.
Hello, everybody. It's my pleasure to welcome my friend, Dr. Roberto Mennitto, to today's webinar session. Roberto is a chemical engineer by training and an adsorption enthusiast by choice. He has spent some years working around structural sorbents analysis for gas adsorption, with particular focus on modeling to predict the performance of structural sorbents in different applications. His main interests involve numerical modeling, techno-economic analysis, as well as combining technology with business development to make technology happen. He received his PhD at the University of Edinburgh, focusing on gas adsorption using monoliths. At this time, he was awarded by the AICHE Graduate Students Research Award in Adsorption and Ion Exchange, a prize awarded by the International Adsorption Society. He then completed a postdoc at Procter & Gamble on machine learning and molecular simulation to study surfactant adsorption, properties for fabric care productions. Afterward, he was hired as a senior system engineer at Corning, where he focused on multi-scale modeling and techno-economic analysis for monoliths in carbon capture. He is now a research scientist at SINTEF, doing research and development work around sorbents and structural sorbents. During the webinar, questions can be submitted to the speaker as a comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome again Dr. Roberto Mennitto and pass over the presentation to them. Please, Roberto.
Hello, everyone, and thank you very much, Giuseppe, for the very kind words of introduction. So I'm very happy to be here today, and it's really an honor to present for the International Adsorption Society. Let me know if you can see my screen.
Yep, can hear you, see you, and see your screen.
Okay. Good. So the topic of today, as said, is going to be on structured sorbents, and the title for today it's actually stolen in part from a publication from your Karger, so it's a lucky chance to present after him. So the aim of today is going to be expecting the ground, so looking at the fundamentals of structured sorbent, and in a way we're not going to look at the most recent literature on the topic, but rather try to see if there is any piece of paper calculation that we can do with simple reasoning that can help us understand how a structured bed works. The agenda will we will quickly look at why we need structured sorbents in the first place, and then we will deep dive into a short course on what I believe personally are the fundamental of monoliths, so the mean residence time and the height equivalent of radical plate, and then we will of course look at what happens when we have non-isothermal conditions, a real monolith, and so on. And finally, we will conclude with just some thoughts from experience on what happens to monoliths when they go from technology to the real world. So how can we make it happen? And I must admit the title of today is on structured sorbents, but we would rather focus on extruded straight channel monoliths, like the one you can see in the images over here, with the idea in mind that anything I'm going to say can actually be translated into many other structured sorbents. And I do want to say before we start that there is a very nice webinar from Professor Reza on the practical side of things, how you structure a sorbent or 3D printing and analysis of data, that I do suggest to look at in tandem with the webinar of today on the topic. So let's look at why we need structured sorbents. Especially in the recent years with the boost in directed capture, the R&D, it's very easy to say that structured sorbents are a very good solution if compared to bucket bed, but actually bucket beds they tend to work rather well. And again, given directed capture, the first benefit that we could think of when it comes to structuring a sorbent is the very low pressure drop and the handling of high flowlets, which is of course a benefit, it's a fact, but I would like to challenge a little bit the status quo and say that possibly pressure drops and flow rates are the least appealing benefit that structuring a sorbent can bring to the system. The first one that I think it's really a true benefit is avoiding fluidization of a bucket bed, and there is actually a very nice paper from Manchester that came out recently where they highlight the issue of fluidization in the context of bucket bed optimization for adsorption. The second benefit is, of course, mass transfer. Most of the applications in gas adsorption tend to be macropore diffusion controlled, so luckily we can tune with a structured bed the thickness of the solid so that we can reduce at minimum mass transfer limitations. But possibly the biggest benefit that we can get on monoliths is heat transfer, because something that was difficult, if not impossible, with bucket bed can actually be unlocked by structuring a monolith, structuring a sorbent. I'm thinking of resistive heating, inductive heating, microwave heating, cross flow of steam in the perpendicular direction compared to flow of flow gas, air, or whatever. So I do think that with the revamp of TSA technologies that happened recently, mostly because of directed capture, I would say, a lot can be done with the heat transfer. And having said, all the benefits, we should always remember that monoliths and structured beds in general, they come with the big disadvantage of cost. They are, of course, more expensive than a bucket bed and also difficult maintenance. It is much more easy to maintain a bucket bed of beads, which is effectively a vessel with beads, rather than panels of monoliths or structured sorbents. So we need to be careful when always claiming that monoliths are always a good solution. Having said why we need monoliths, we can now go into this crash course on the fundamentals of monoliths. And the best place to start is from a virtual breakthrough experiment. So we just look at the mean residence time. We're all familiar with breakthrough experiments. We have a bed in which a portion of it will be filled with a sorbent, and we flow a gas within the bed, and we monitor the concentration over time with analytics. And we can write a mass balance and write basically what is the equation for the mean residence time, which is going to be proportional to the length of the bed, the superficial velocity we flow inside the bed bed voidage, the bed density of the sorbent, and the amount adsorbed over the concentration of the gas that you are targeting. And here I give some average values of density, bed voidage, and superficial velocity that we would find in packed bed applications versus structured bed applications. If we look at the mean residence time, only a breakthrough curve would look like this for a packed bed. And of course, if you switch then to lower bed density, because of course structuring a bed means lower bed density, the mean residence time will be faster. And if we go then to much faster velocity that we want to have in a monolith compared to a packed bed, we saw that the mean residence time is significantly less than the one of a packed bed. And this already, with this simple analysis, we can already draw two conclusions. The first conclusion is that although structuring a bed can improve our cycle time because it can become much shorter, sometimes the timing of our absorption process might be dictated by the mechanics around the bed, so the opening and the closing of the valves, or rotating in case of rotating valves. So we need to be careful in saying that we can improve by a lot the reduction in cycle time, because sometimes we don't care about the mechanics, which are actually quite important. The second aspect that I would like to point attention to is that when we are in a lab and we take a breakthrough rig that is designed for a packed bed and we just change mass flow controllers and we use a monolith, sometimes the monolith response might be very close to the blank of the breakthrough. So my suggestion is be careful in how you run breakthrough experiments on a monolith, because sometimes this might happen. And here we have the picture of a very nice book that I suggest if someone wants to have a deep dive into how mean residence time can be useful to design absorption processes. So we warmed up a little bit with the mean residence time, but the actual core of the presentation for today will be around the height equivalent to a theoretical plate. The HETP. So what is the HETP? Before we have seen that a monolith or a packed bed can have a breakthrough, so a lagging time on the concentration response, but we are all familiar with the concept that the breakthrough will have a certain dispersion, and the dispersion will be caused by many factors. So what we can do is to say, okay, we have our breakthrough from either a model or experiments, and we can calculate the mean residence time, but we can also calculate the variance of the breakthrough curve. And if we divide the variance by the square of the mean residence time, we obtain the HETP. So in a way, the HETP is the normalized variance of the breakthrough curve, meaning the higher the HETP, the broader is going to be the breakthrough curve. So in a process, we will try to optimize it in a way that the HETP is very small, so that the dispersion is kept at minimum. And of course, this is the very popular plot that you find sometimes, which is basically the HETP versus either velocity or a Peckley number, where you see that there is a minimum and then the HETP comes up. And there is a very nice work from Rutten and Deron that, to my knowledge, is the first paper that came out discussing use of laminates in gas separation, that shows how to derive the HETP. So let's work a little bit in the paper. So what Rutten and Deron did, they were using as a case study a parallel passage conductor, which is effectively laminates, with a Z direction for the gas flow and an X direction for the diffusion into the solid here, with a solid having a thickness W. They take the 3D space and they simplify it to a 1D plus 1D domain, where the first dimension is the Z dimension, so the gas flow within the free space of the channel, and the second dimension is the dimension of diffusion within the solid. And assuming that this system is isothermal, it has a linear isotherm, and the pressure drop are negligible, they basically wrote down mass balances. The first mass balance is the overall mass balance of the solute in the system, which accounts for the axial dispersion term, the average velocity of the convective term, the accumulation in the gas and accumulation in the solid. Then we have the mass balance on the solid, which is basically the diffusion in a slab over here. This is the equation of diffusion in a slab. And then on the boundary where x is equal to 0 here, the gas-solid interface, we write the isotherm. So the amount adsorbed is equal to an Henry law constant times the concentration of the solute. And they introduce a very useful factor, which is the retention factor small k here, which is equal to 1 plus the channel voidage over the channel voidage times the Henry law constant, which is effectively a ratio of how much sorbate is in the solid over the sorbate that stays in the gas. And if we take these equations, we go in the Laplace domain, we solve the equations for Q, the average amount adsorbed and the concentration, and we apply the van der Waals theorem, we can calculate the mean residence time of a breakthrough curve and the variance of it. So with variance and mean residence time, we can calculate then the HTTP. And these are the images of the appendix from Ruttwen and Ron paper, which discussed all the mathematics behind. So let's have a look at how the HTTP correlation then looks like. The HTTP correlation for a monolith is sum of three main terms that we will call resistances. The first resistance that we see here is the resistance given by the axial dispersion, and it's proportional to the molecular diffusivity of the basically a molecule in the free channel over the average velocity that we flow in. The second resistance is the resistance given by the diffusion within the solid. So we see here the retention factor. W again is the thickness of the solid, and the S is the diffusion in the solid system over here. And then the last one is the resistance given by the velocity profile. So within the channel, we will have a certain velocity profile. And this is the resistance of it. Cm is the Taylor-Harris coefficient that we will see what it is in a moment. H squared is basically the channel opening squared, the M, the molecular diffusivity, and the average velocity. The equation that you see over here, it's the HTTP for what I call the flat geometries. Flat geometry is any geometry where the diffusion happens in a slab. Effectively, we can reduce the diffusion into the solid as if it was in a slab. An example is the square channel. It can be the triangular, the diamond shape, or the laminates. When it comes to round geometries, for instance, an hollow fiber or an hexagonal channel with this type of coding, we need to use a slightly different equation, and the only difference between these two lies in how we define the resistance into the solid. Basically, what is the main difference? The difference here is that the diffusion will happen in a sort of cylindrical system. So there is an addition of an F term that you can find in literature, but it's basically this F term accounts for the diffusion within a cylindrical coordinate. So what we're going to do now is to have a look at what is the Taylor-Harris coefficient, have a look at how we can write the solid resistance, and then look at some results of this correlation. So the first thing we will see is the Taylor-Harris dispersion factor. So this is a topic quite dear to liquid adsorption or chromatography, because basically this resistance tells us what is the effect of the gas side of things on the HTTP. The Taylor-Harris for a flat geometry can be written again as three main terms, term 1, 2, and 3, with the functions G1, G2, and D3. And G1 is the function that quantifies the effect of wall retention with a uniform flow. What does it mean? If we have a gas channel and we flow a step concentration inside, and we assume that the velocity profile is effectively a plug flow, there will still be an effect on the gas diffusion because of wall retention. And this is what quantifies G1. G2, on the other side, is the opposite. What is the effect of dispersed flow because of velocity, assuming that there are non-adsorbing walls? And then the last one, G3, is an interaction term between the two. And there is very, very good literature from Dutte and Layton on the topic that I do suggest reading if interested in the topic. For round geometries, I report a very useful correlation that is basically the Taylor Iris for a hollow fiber with adsorbing walls in the case of a perfect circle as a free cross section. So this is what concerns the Taylor Iris dispersion. Now, the big problem in gas adsorption, which is the field where I work, it's how to define the solid resistance. And there is work done in 2005 by Anne and Brandani on rewriting slightly the resistance into the solid. So what did they do? They took a square channel and they ran 3D simulations of a gas flowing within this channel and calculated the HTP. And the dots here are the 3D simulations. What they did, they took the HTP correlation I showed you that was available in literature, and they, with great surprise, they realized that the HTP, the solid line here, was not fitting the 3D simulations. So the first thing they did was to split the contribution of solid resistance over fluid resistance, so axial plus velocity profile, and they noticed that for their system, the solid resistance was dominating the HTP. And maybe in this plot is a bit extreme, but we could generalize, saying that for gas adsorption systems, the problem is often the diffusion into the solid. So what they realize is that the gap between 3D simulations and the HTP correlation was in how they were translating the 2D diffusion problem, so a molecule that diffuses horizontally first and then vertically, into the 1D plus 1D that we have seen from Rutten and Ron. So in the schematic that then drives the equations of the mass balance. So what did they do? They took the square channel with the solid around, and they noticed that the solid area could effectively be split between sides, so the solid that is perpendicular to the perimeter, and corners, so an area that does not touch directly the sides of the square channel. You see here now, we have 4 sides and we have 4 corners. What they did then was to say, okay, what we want to do, we want to keep the volume of gas constant, so the white one here, but we want to redistribute the solid corners on the sides, thus reducing the diffusion, the 2D diffusion problem, to a 1D diffusion problem. So now what we have is a diffusion in a slab, effectively. And they introduced the concept of corrected thickness, which is basically the thickness of the solid that comes after redistributing the corners of a geometry. And if when they wrote basically the HTP accounting for the corrected thickness, they were able to basically match the 3D simulations. And work that we have published in 2022 shows how to derive the corrected thickness for any arbitrary geometry. For instance, here, for a flat geometry, what we effectively do, we redistribute the area of solid over the wet perimeter of the free cross-section. An example here is for a triangular channel where we take the corners and we put them on the sides. On the other side, for round geometries, especially the hexagonal channel, that is a quite practical application, this is the equation that one has to use, where basically, again, we take the portion of solid that is not in direct contact with the free cross-section and we redistribute it around the hollow fiber. So just to see what we can do with the HTP then, we can kind of reverse engineer the HTP to write a simple numerical model, much similar than 3D simulations, that we can use, for instance, to match breakthrough experiments or to use it in process simulation. So what we can do, again, we take the reference system from Rutten and Ron, so a dimension for gas flow and a dimension for solid diffusion, and we write the overall mass balance. The mass balance on the solid and the average amount adsorbed. Now, this time, the mass balance on the solid accounts, of course, for the diffusion in the solid. For the diffusion in the slab, we use only this term over here. For the diffusion in a round geometry, so an hollow fiber-like diffusion process, we will add also this term over here. And in this model, all the parameters are fixed, the bed voidage, the average velocity, diffusion in the solid, and so on. We only lack 2 parameters. The first parameter is how thick is this solid over here, but this is quite simple. It's the corrected thickness. So what we will use to calculate the average amount adsorbed is the corrected thickness. The last parameter is the axial dispersion. So how do we write this axial dispersion over here? And again, to write it, the HTTP comes to help. The axial dispersion, we can write it as the sum of axial resistance and velocity profile resistance times average velocity over 2. And if we take this from the HTTP, we end up basically with this correlation, that the axial dispersion is equal to the molecular diffusivity of the gas in the channel times 1 plus the Taylor-Harris coefficient over 2 times the Peclet number squared. This is the Peclet number here. And I hope that this equation looks familiar because it is often reported in literature as Taylor-Harris correlation. There is only something that we need to pay attention here. It is often the case that the correlation accounts for the Taylor-Harris coefficient being equal to 1 over 96. As I have written it over here. This is what you would often find in literature. And this way of writing it, it is correct, but it accounts for the dispersion of a gas in a channel without adsorbing walls. So this correlation, there is a very nice paper from Harris from 1956, where it shows how to derive this correlation. Problem is that when we have a channel with adsorbing walls, we need to account for the correct Taylor-Harris coefficient. So for instance, in the paper of Harris from 1959, a bit later than this one, he accounts for adsorbing walls. So we have a solid that adsorbs on the side of the channel, and he arrives to this Taylor-Harris coefficient. And if you notice this equation, if the retention factor is 0, so there are no adsorbing walls, we reduce the Taylor-Harris to 1 over 96, which is the same as this correlation. But if there are adsorbing walls, we need to account for the retention factor. So we will have to use this equation to estimate CM. So pay attention to not using this correlation for adsorbing case when using monoliths. And again, in the paper we published, here reported the hollow fiber case, but we reported all the equations to calculate the Taylor-Harris coefficient for many other channels. So we now have the axial dispersion, we have the corrected thickness. Now we can check if this model that we can, for instance, code in MATLAB, Python, Fortran, whatever language we like, we can check that this model matches maybe experiments or 3D simulations. And this is the work that we presented then in 2022. What we did was to, again, run 3D simulations of different channels. You can see the dots in these plots are 3D simulations. And then we used the model from the previous slide to predict the breakthrough. And you can see that the solid line, so the simplified model, predicts quite well the 3D simulation. So it means that if we account for the correct axial dispersion and the correct thickness of the solid, we match both mean residence time and the variance of the curve. It should be noted that an even simpler model, in this case for an isothermal and linear system given by Giddings in the early 80s, can also match quite good this data. And I do suggest of trying this equation to match the results. So before we go to non-isothermal conditions, I just want to draw the attention on something that is very often cited for linear driving force correlation. So when we write numerical models, often we use linear driving force approximation for the diffusion in the solid, and it makes sense. And there is a nice paper from 2004 from Patton and co-workers where they tried to derive the linear driving force for any arbitrary channel of a monolith. What they did was to basically assume that the surface area of a channel, here again I use the square for simplicity, so the surface area of the channel and the area of solid would be kept constant, and that all geometries could be reduced effectively to a hollow fiber. Now, these two assumptions, they work well in the case of round geometries with thin walls, but it should not be used for flat geometries like square channel, triangular, diamond, and so on. And I'll show you why. If you take these assumptions and you go from the square channel to a hollow fiber, you firstly increase the size of the free channel. So this might have implications, for instance, on the pressure drop. And what happens is that you change the bed voidage, because to have the bed voidage unchanged, you need to keep the solid volume constant, but also the volume of the free space. And if you change the bed voidage, you also change the retention factor. And here I took some parameter from Anne and Brandani work. I took their Henry constant, and you can see here that I can calculate a retention factor for the square channel. And when I translate it into a hollow fiber with the assumptions of Patton and co-workers, I have a new retention factor. So pay attention that this can have a big effect. And if we write the HTTP correlation and we notice effectively that in the resistance of the solid, we can rewrite it as this term times 1 over a linear driving force coefficient. We can take the linear driving force coefficient from HTTP, which is a corrected thickness squared over 3ds, or we can take the LDF from Patton. I do not report it because it's a rather long equation, but you can find it in their paper. And if you write the HTTP for Patton or the one I show you here for the square channel, you can see that there is a big difference. And in the paper we published in 2022, I report also this behavior, for instance, for the triangular channel, where the approximation of Patton and al overestimate the HTTP. So again, it can be used as an approximation when it comes to hexagonal channel with thin walls. But in any other case, I would suggest to use the corrected thickness. So now that we have basically checked isothermal and linear conditions without pressure drops, it's time to relax the assumption of isothermality. So what I want to do here is, to say, okay, realistically in some applications we will have a temperature swing because of non-isothermal effects, so we want to write an energy balance of the monolith. And often you will find in literature this is the expression of an energy balance. I'm not going into details, but basically the idea is similarly to what we have done for the overall mass balance on the mass side before. There are only two parameters that we don't know in this case. The first one is the thermal axial conductivity, and the second one is the heat transfer parameter monolith to walls of the column. Then the other ones, I don't know, the capacity or the heat of absorption, they are all fixed by the properties of the solid. Now, when it comes to thermal axial conductivity, we can draw an analogy with axial dispersion and say that the thermal axial conductivity is equal to the thermal conductivity of the gas that we are flowing times 1 plus the Taylor-Harris coefficient over 2 times the thermal Peclet number squared. That accounts, of course, for heat capacity and the thermal conductivity of the gas. A bit more tricky is how we define the heat transfer coefficient monolith to wall. And actually, always in 2005, there is a paper from Boger and Heimel that beautifully shows how to calculate this parameter. So what they did was to take as a reference case a cylindrical monolith that is basically plugged into a wall, into a casing that you can see here in black. And they said, okay, what happens if I want to transfer heat from the center to the side? We will have the monolith resistance, of course. Then between the monolith and the wall, there will be a little gap of air that happens when you have a monolith in a casing. And then there is the wall of the column. And this is how the profile of temperature would look like. There would be a uniform temperature inside the monolith, pretty much. Then there will be a big temperature drop in the gap of air that acts effectively as an insulator. And then, of course, a temperature gradient within the walls of the column. So what they did was, okay, what we want to calculate, they said, okay, we want to calculate the heat transfer coefficient monolith to wall, knowing that we have a resistance incidence problem. The first resistance is the monolith one, and then the gap. So HW can be written as 1 over the heat transfer of the monolith plus 1 over the heat transfer of the gap of air. The one for the gap of air is easy to write it because it's the thermal conductivity of the gas that is inside the gap over the gap thickness. And when we use this gap thickness, we could fix it sometimes because we know how many millimeters or microns are between a wall and a monolith, but I would just suggest to relax a little bit this fixing. If you want to fit a temperature gradient, you can just relax a little bit this gap thickness. The other one, the heat transfer of the monolith, they say, okay, for a cylindrical monolith, it can be written as 8 times the radial thermal conductivity of the monolith over the diameter of the monolith, the m over here. Now, the problem is how do we write the radial thermal conductivity of the monolith? And from this one, there is a beautiful work from Groppi and Tronconi on how to calculate the radial thermal conductivity. So what they did was, again, to take a representative channel of the monolith and to ask themselves the question, what is the resistance is that the heat flow is going to see if it travels from left to right. So if we have a hot source here and a cold source, the flow will firstly encounter the resistance of the left side wall of the channel, this resistance over here. Then going from left to right, it will find the top and bottom walls of the channel with the free space over there. So these are the three resistances in parallel. And finally, the right side wall will provide the last resistance. And if you draw the electrical analogy of this one and try to follow the paper, you end up basically with this correlation. The radial thermal conductivity is proportional to the thermal conductivity of the solid here, the thermal conductivity of the gas, and the bed voidage, so the channel voidage of the system. And this correlation can be written for many other things. There are other papers from Groppi and Ronconi that report, for instance, the same correlation for a triangular channel. Or even better, they report the same correlation for a square channel with a coating. And what you do effectively, you just add inside the correlation the volume occupied by the coating. So if you want to know more on these correlations, I do suggest reading the papers from Groppi and Ronconi. So now we have these two. We have the axial thermal conductivity. We can basically run a numerical model with the mass balances and the energy balance. Here I take just an example from my PhD work. I modeled a corrugated channel monolith. This is actually a monolith reported by Professor Ritter. And I assume that the monolith was made of 13x zeolite and would absorb CO2. And I was simulating, firstly, the problem with the 3D simulations in COMSOL, and then using a simplified model as the one before, plus the energy balance. And what you can see over here is that the dots again are, the symbols are 3D simulations for the mass in black and the temperature in red, and the solid line is the simplified model with the new energy balance. You can see that if we carefully account for all the parameters and we write thermal conductivity, axial thermal conductivity, and axial dispersion with the correct Taylor-Harris coefficient, we predict rather well the temperature and the mass profile. I just report as well in the thesis what happens if we just use the Taylor-Harris often reported in literature equal to 1/96. You see now that the mass profile and the temperature profile are much sharper than what they should be. And don't get me wrong, I'm not saying that the solid line in this plot is a bad prediction and so on. I would say it's decent, but of course, if we have correlations to estimate the Taylor-Harris coefficient, we can even better predict the 3D simulations. So I hope that this convinces you that with careful look to the system that we are investigating, we can rather well predict what is going on. There is an implicit assumption that I made that I didn't tell you, that it's time now to challenge. And the assumption that we have made so far in our discussion is that any monolith we take can be an exact replica of a unit cell, which is a single representative channel. But we know by experience that this is not the case. Even the most perfectly made monolith will have heterogeneity in channel size and wall thickness. And how can we make some reasoning out of it? Again, we look at the HTTP. And there is beautiful work done by Kassler and co-workers in the early 90s, looking at the same problem for a bundle of hollow fibers for chromatography. And in my opinion, the best reference on the topic is this one from Schisler that really beautifully explains the problem. So what they do, basically, they say, okay, we have an arrangement of channels that are circular, so hollow fibers, and each fiber has an average radius over here. And the bundle of fibers is going to have a certain variance over the average radius, which the model has a Gaussian distribution. They introduce also useful parameter, which is the normalized variance called epsilon 0 in their case. What they do, the first thing they do, they calculate what would be the average velocity in many fibers compared to the average velocity that we would get out of a system if all the fibers had exactly the average radius. And with surprise, they notice that the average velocity of a real structure is not the average velocity from the average radius. It is the average velocity of the average radius times a factor depending on epsilon 0, the normalized variance. And when I read these results, I actually could not believe it was true, and I made the math myself and ended up exactly in the same function. And to me, it's really beautiful, this result, because intuitively I would imagine that eventually the average velocity is the same. And if you actually run a numerical model of many channels, then you average the results, you will see that keeping constant the amount of solid in the system, you will end up with an earlier mean residence time because the average velocity is faster. Then the second big result from the paper is from the HTTP. So what they did, they plotted effectively the HTTP on the y-axis and reduced velocity on the x-axis. And in solid line, you see the HTTP for hollow fiber without any dispersion, so a perfect ideal monolith. And then you see here that increasing the amount of epsilon zero, so basically broadening the variance of the Gaussian distribution, you have an increasing HTTP, which means the more real is the system, the bigger is going to be the dispersion in your breakthrough curve. And this problem, this poses a big challenge for us, because when we do experiments in a lab and we run a breakthrough experiment, for instance, with even a small monolith of few channels, we are often within these ranges of conditions. So effectively, what we measure in a breakthrough experiments is more the distribution of wall thickness and channel size rather than an actual mass transfer constant. And this is a work that we also realized while in Edinburgh. Colleague Ishan Sharma basically investigated the effect of a real monolith and flow maldistribution to predict process performance. I guess it was a pressure vacuum swing adsorption system to separate CO2, and there were experiments available in literature on purity and recovery from the process. And what he did was to take a breakthrough that was available on the monolith and pass a linear driving force coefficient to match the dispersion. And if he was using the same linear driving force coefficient to predict purity and recovery, was ending up very far from the experiment. So the model with the mass transfer from the breakthrough was totally a failure, effectively. On the other side, if he was fixing the mass transfer to the one of CO2 in 13x and using the breakthrough to basically quantify flow maldistribution, then he was basically able to predict the purity and recovery from the process. So the big message that I want to pass here is pay careful attention when you extrapolate mass transfer of a sorbent from a monolith, because possibly what you are seeing is just the flow distribution and the effect of channel size. To mitigate a little bit the effect, what you can do is to take fragments of the monolith and run, for instance, volumetric experiments or a gravimetric or a zero-length column. In case of coated monoliths, you can take dried coating and try to run experiments on the dry coating to understand the mass transfer. It is not the best thing. Of course, it would be nice to run just a breakthrough, but it's possibly the best way to mitigate such a problem when it comes to monoliths. So, to conclude the survey on real monoliths, there is a nice paper that came out recently from Classens that investigated not only the effect of a real monolith on HTTP, we have already seen it from Schisel, of course, but investigated the effect of a real monolith, for instance, on a simple 4-step VSA process. And he noticed that a real monolith would always worsen the key performance indicators of the system, like recovery, the throughput, and the energy consumption. So the higher is the variance on the channel size, the lower is the recovery, throughput, and the higher is the energy consumption. The purity remains quite unchanged, mostly because it is an indicator related to sorbent interaction more than channel distribution. But I do suggest reading the paper for further information on real monoliths. So, we have concluded the survey on HTTP, isothermality, real monolith, and so on. And I just want to pass some thoughts that I have on monoliths that are just not technical. So often in literature we can find techno-economic analysis on bucket beds or monoliths, but sometimes this techno-economic analysis is not translated into business. And I hope that young graduate researchers or fellow colleagues will realize that anything we have said so far in this presentation stops at the very bottom level of decision making. There is a very nice paper from Lapkin in 2004 where they investigate the possibility of using an activated carbon monolith for VOC removal in printworks industry compared to the conventional incineration of them. And they come up with a series of decision-making levels from product to infrastructure and society that are quite interesting. This is basically what happens in a company when you want to go after a certain technology. Okay, the technology is better than the benchmark, but technology is not the only thing we need to look at. And when it comes to monolith especially, the big decision has to be made, for instance, on life cycle assessment, environmental impact. The reason why I say it is that to make a monolith, either in an extruded of active material, 3D printed or coating on active material, there are many steps that we take. Again, from the same paper, they highlight all the steps then we need to take in order to produce an activated carbon monolith. And the steps are a lot, meaning there is a lot of energy going on, environmental impact, people that have to be paid to do the thing. So actually the cost of a monolith is important, but also its environmental impact. And also especially when it comes to coating or active material, what is the coating cost? What is the reusability of the monolith? Can the coating be reactivated or we need to burn it? So there are many decisions that we need to take that are not considered from techno-economic analysis only. And I hope problem of this is I do acknowledge that finding how much a monolith costs or what is the environmental impact is difficult. That's why the literature is scarce. But I hope that more paper will come out addressing what is the impact of structuring a bed on process performance more than sorbent only, because structuring of it can be as important as the active material we are using. So, to conclude the presentation of today, I don't really have any major technical highlight that I want to conclude with, but if not, some things I learned while being in the topic in the field of monoliths. The first thing is, I summarize it as work before you run. So make sure to master really mean residence time and HTTP before you rush into numerical simulations, because it's very appealing to just run process models and try to make sense out of it. But it's more fruitful if you spend some time doing piece of paper calculations. The second one is pay attention to experiments. As we have seen, a breakthrough experiments might mislead the judgment on mass transfer. So it's monoliths, they actually unlock new problems for the UPAC task force on diffusion measurements. So in future, I'm sure there will be new papers coming out addressing this issue on how to directly extract mass transfer from structure sorbents. And the last one is the topic of monoliths is actually much older than what we may think. In the adsorption community, we have beautiful works from Professor Ritter, Professor Yuri Denayer, Arvin Rajendran, Paul Webley, Stefano Brandani, and so on. But there are many, many papers from chromatography, catalysis, heat transfer applications. So make sure you have a look always at these fields, because a lot of interesting things are happening there that we could take advantage of. So my work is over for today, and let me just conclude with acknowledgements. And this presentation was also done thanks to the support of colleagues from SINTEF, and SINTEF this year is celebrating 75 years from opening, so happy birthday, SINTEF. Let me also thank the Professor Brandani for initiating me to this world of monoliths in adsorption, and all the people from Edinburgh that supported it. And I hope that my mom, dad, and my brother will now understand what I make for living on a daily basis. And yeah, let me say that this talk is dedicated to my wife Gaia, that really supported me during the preparation. Forza Napoli, and I hope you enjoyed the webinar, and I would be happy to take any question. Thank you.
Hello, Roberto. That's a very interesting presentation, and totally agree with you with the last sentence you said about Forza Napoli, our football team. We got quite a few questions from the YouTube webinar. I'll go through them as they came. So let's start with Benjamin Clansens. He says, "Hi Roberto, very interesting. Could we imagine to produce a monolith with a packing density or equivalent bed porosity equal to that of a packed bed? Or would this not be interesting?"
Well, no, it would be interesting. So you can produce a monolith that has a bed voidage similar to the one of a bucket bed. It would still have a slightly lower pressure drop just because the flow path is straight and it doesn't have the tortuosity of the bucket bed. The thing is that it is difficult. In practice, when you extrude a material, an active material, or when you coat a material, you need to coat so much or engineer so much the extrusion behind very thick walls that is really not worth doing it. The capital cost of just producing such a monolith might not be worth it. I don't have exact numbers, but I would imagine, for instance, to have a monolith and we coat very thick walls, it would require a lot of coating steps, and each coating step is dollars. So I don't think it will ever be achieved in reality. Maybe it's possible, but I don't think it will find any useful application for it.
Thank you. I hope this answered Benjamin's question. Then there is Kian Karini. He's thanking you for your very interesting presentation. And he was wondering if it is possible to use the diffusion calculation relations in monolith to calculate the linear driving force for conductors figurations.
Linear driving force of monoliths for what types of
conductor figuration. So I guess he wants to say to turn the diffusion calculation relation in just a linear driving force coefficient.
Yes, it can be done. It can be done. I can show you. When you have the HTTP correlation, I actually have it here from the slide of LDF. So what you do effectively, what you write is a linear driving force equation where the derivative of the average amount adsorbed is equal to the LDF from the HTTP, so here, times the difference between the amount adsorbed from the isotherm minus the average amount adsorbed. And it basically comes from the HTTP. So it's the LDF would be 3 times the diffusion of the solid over the corrected thickness squared. And this would apply to flat geometries. In the case of round geometries, it might be useful to look at the HTTP from a round geometry that we have here. Let me just here. So again, the linear driving force would be the diffusion into the solid over the this term over here squared, which is basically D is the diameter of the equivalent hollow fiber, W is the thickness of the solid, and the F parameter over here. You can find this F both in my paper, but of course in the work of Schisla, Kassler, and co-workers for hollow fibers. So any paper on hollow fiber, even Harris, you would find this one. So I'm quite sure that the linear driving force for a round geometry would be ds over this term times F parameter.
I'm not sure if I missed it or not, but what about in case of a corrugated monolith as the one you had in your...
Yes, so the corrugated monolith, I can show you from the image. So the corrugated monolith, that's a bad question because my professor would blame me for not publishing the results again. So, but I can show you. So corrugated monolith is challenging because you see here, this is the unit cell. And the light gray area is the solid that is touching the perimeter of the free cross-section, while the dark gray area are the corners of the geometry. In my PhD thesis, you can find basically a simple algorithm to redistribute this dark gray area over the sinusoidal channel. And they give also very simple correlations. You give the size of the sinusoidal channel, the thickness of the solid, and you can calculate what is the corrected thickness for the sinusoidal. And this is a flat geometry. So you can use the linear driving force equal to 3 times the diffusion of the solid over the corrected thickness squared. So if you look in my thesis, it should be available online. You can find the correlation also for the sinusoidal channel.
Thank you, Roberto. Following up, why should we expect worse performance in monolith structures compared to bucket bed if we don't do what you said?
No. So so monoliths will they not behave bad. They just behave different from a bucket bed. So I think what I struggled the most when I started working on monoliths was that most of the literature works with bucket beds. So a lot of what we are used to in terms of thinking it's inherited by packet beds. So we just have to switch on thinking that monoliths behave differently. Monoliths have much faster mean residence time, and the dispersion is different from the one of the packet bed. For instance, how you trade off mass transfer with a pressure drop is different in a packet bed than a structured bed. So the message for today was pay attention when using a monolith, because something that you would assume is correct because you studied in packet bed might not apply in structuring it.
Excellent, thank you. We have another question from our audience on YouTube by Sunny Pawar. He's asking, in your first slide, you mentioned the most significant benefit is with the heat transfer. Are there any experimental validations of this claim in your studies?
So I would say yes. So again, this was a bit of a challenge to what we are used to hearing from pressure drop, especially because the adsorption community is heavily involved now in carbon capture, and especially directed capture. The main problem there is low pressure drops. But you can find a nice work from Professor Denayer where he uses, for instance, alternative heating mechanisms when structuring a bed. And there is also there is a book from Mullin. Unfortunately, I don't remember well the names, but there is a nice book from Mullin and another author where they investigate the use of flowing in laminates structure, flowing gas in one side, but then cross desorbing with steam on the other side. So even resistive heating, if you think about it, a packet bed of activated carbons might easily burn because you form closed circuits in the packet bed, while structuring a bed allows you to transfer it from the sides or from the inlet and outlet. So I do think that the main benefit that we will see will be in temperature swing while working with heat transfer. And again, it's a personal statement that is literally supported by literature, but I hope that we will find more literature on that.
Thank you so much, Roberto. If you still have time, there's one question left. Always tagging along what you said earlier, that most of the studies previously have been done on packet beds, and so most of commercial software are. If I am a graduate student and I am approaching to a monolith simulation, but I have a commercial software that works only for 1D packet bed, how can I transform the monolith in an equivalent packet bed? Is there any characteristic length of the diameter of the particles or something like that?
Yeah, of course. Yeah, of course. So the first thing you can do, for instance, if we look at the let's say the system here, yes, okay, is so the first thing you can do, for instance, is to set the isotherm would be exactly the same. The equations that you use are exactly the same. What you want to change is the linear driving force coefficient. As said, it's going to be the one using the corrected thickness. So instead of using the bed size in diameter or radius, you use the corrected thickness. And remember that the linear driving force for a packet bed is 15 times diffusivity over length squared. For a diffusion in a slab is 3 times the diffusion over the length squared. The other thing is you use the axial dispersion correlation that we have seen from Taylor-Harris. So you don't use the axial dispersion from a packet bed, but you actually use this convention, and then you use here, I'll just share. Yeah, this one that we calculated. So you use this correlation for the axial dispersion. And again, molecular diffusivity, you know it, the average velocity, you know it, the opening of the channel, you know it from the system, the Taylor-Harris coefficient you can find in literature from my paper, but also others, the Taylor-Harris for any arbitrary channel geometry, so you can calculate the axial dispersion. From the energy balance, you can calculate from the energy balance, anything you need to change is the axial thermal conductivity from this correlation, the heat transfer monolith to wall with the correlation I showed in the presentation. you are basically done. The last thing left is the pressure drop. You turn off the squared term in the ergon, you are left with the linear, and the linear you can use the Fanning-Reynolds product for a pressure drop in a channel. I'm quite sure you can even find it in Wikipedia. It's such a popular equation, and there is a nice work from Shine London reporting pressure drop for all the different types of channels. You can also write me an email. I can show you a bit more in detail how I usually do the equivalence in a way.
Excellent. More questions are coming from the YouTube channel. Shanmukh Ravuru is asking if, of course, he's thanking you for your webinar, and he's wondering, in a wash-coated monoliths, part of the adsorbent is in the wash-coat layer, while the rest is within the monolith walls. Does the adsorbent inside the walls contribute to adsorption?
Of course. So anything we have said so far, that's why I kept this presentation a bit more general on this side, because anything you do effectively, when you have your coated monolith and you have coating and the wall of the backbone structure, you can calculate basically an effective length of the wall, which is going to be the one that you see over here. So this one is going to be coating, maybe a part of it is going to be coating, and part of it is backbone structure of the monolith plus the slurry coating inside. So you can always calculate a corrected thickness for the effective thickness of the monolith. So you can still use HTTP correlation for a coated monolith. You just calculate the effective thickness because of coating. So maybe your monolith is 200 micron wall plus 200 micron of coating. So the total is going to be 400 microns.
Okay.
I actually did some of these calculations. It's equivalent. It's equivalent. So it's not a problem if you use either extruded or coated monolith. Actually, most of the time you would just coat on a monolith rather than extruding. So it's a very good question, this one.
Yeah, at this one I have about extrusion. I have another follow-up question by Brick Vorex Straight. I'm sorry for spelling it wrong. He says, of course, he thanks you, and he says, indeed, it's crucial to look at the impact of the old TEA. When mentioning the large energy impact of processing the monoliths, is this linked to the extrusion process? Better to use laminates?
Yeah, so the idea is it is linked to the production of a monolith, and I'm you know the classical way of making a monolith might be just extruding what is called a green piece of material, and then you basically put it in a furnace to calcine, and then you get what is a monolith. So a lot of energy will go into heating up the gas into the furnace, for instance. I'm honestly for acrylic carbon is actually let me just skip quickly. It's actually quite nice to look at this one, because you will see I do suggest reading this paper, because you will see that most of the here you see in each step there is there will be energy vectors going in, and you will see that I think most of it is going in incineration and activation of an acrylic carbon monolith. So for laminates, I'm really sorry I don't have an answer, because I'm not familiar in the way they are produced. But again, I know, for instance, there are some laminates that are made of carbon, so I would assume it's similar to this one, and I've seen other laminates that are made of inorganic, like silica material. So I would assume that it's similar to extruding a monolith. So a lot of energy will go in going from a green material to a finished one. So the burning of it. But again, if I'm not an expert into manufacturing of monolith specific, I just have basic knowledge of it. But I do hope I see a lot of literature that explains the impact, for instance, of sorbent properties on whatever process. Problem is when you structure it, unfortunately, we still have a lot of uncertainty on what is the impact of just structuring it. So I hope that someone will publish at some point TA accounting for the structuring and what is the share of cost of that on the total. No, I hope it answered the question. I'm sorry if I don't have more information on laminates. Giuseppe, can you still hear me?
Yes, Roberto. I'm not sure what's happening with Giuseppe's mic, but
Okay.
I think we now have answered the questions. I'll take the screen back and do the outro. Right. Thank you, Dr. Roberto Mennitto, for your presentation, Structured Sorbents, Inspecting the Grounds. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feeds and our other associated pages. The hope is that the work here discussed today will be a useful resource for the adsorption science community in the future. The next confirmed IAS webinar will be given 2 weeks from today by Dr. Meinier van der Spek on March 12th at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed, LinkedIn page, and through the IAS mailing list. With that, we thank you for joining us and hope that you will join us again soon.